just our last bit then on curves. I'm just running through a few examples of some common curves that are already drawn here. I just thought it'd be useful so you could see these. So the graph is as follows. So it looks like this. That's just a circle, despite my diagram. It's a bit flat looking, but it's supposed to be a circle. This is an example of a curve r equals a cos theta. We've already drawn one of those in the example. So which is a circle, so that's fine. Notice r equals a cos theta, or line of symmetry running along there. This one here, this is an example of a more general curve, r equals a sine n theta, where n is odd. This is an n leafed rose. So if that was 5, there would be 5 leaves into this rose. In this particular case, then that one would be 3. So that's that example. Number 3 is also a sine one. Again, our line of symmetry down here because it's sine. This is an example of a more general case, r equals a sine n theta, where n is even. It is an example of a 2n leafed rose. So here, if n is 2 here, then you're going to get 4 leaves as in a 2n leafed rose. Graph then as follows. This is an example, a more general form. That's a cos n theta, where n is odd. It is an n leafed rose, very similar to the sine one. Sine has its line of symmetry here, cos has its line of symmetry here. N leaf, so this one's going to be a cos 3 theta. If it was 5 theta, there'd be 5 loops, and so on. Again, similar to the previous one. R equals a cos n theta, where n is even, and again it's a 2n leafed rose. So in this particular example, because there's 4 leaves, then n must be 2. This graph is as follows. This is an example of a more general curve. You can see it okay, where r equals a sine squared theta, which is called a lemniscate. Graph as it follows. An example of a more general curve, r equals a cos squared theta, which is also called a lemniscate. This next one then, this is an example of a more general curve, r squared equals a squared cos 2 theta. Is another example of a lemniscate, but since r squared cannot be negative, there are no points on the curve in the intervals between pi over 4, which is 45 degrees, and 3 pi over 4. So there's your angle there, and there's nothing all the way back down to there. And then down here, it's the same deal. This curve then is as follows. This is an example of more general curve, r squared equals a squared sine 2 theta. It's another example of a lemniscate, but since r squared cannot be negative, there's no points in the curve in between pi over 2 and pi over 2 and pi, or between 3 pi over 2 and 2 pi. Or we would maybe have that going to negative going on there. A slightly different looking one then. So this is an example of a more general type of curve, r equals a theta. Very straightforward looking formula, but that gives us an Archimedean spiral, so it just works its way out then from the center. Just a few further notes then on this. So r equals 2 sine theta, so we should know, sorry you can't see that, r equals 2 sine theta, we should know of course that's going to be a circle. We recognize that, and the circle sits up here with our line of symmetry then going down there. If we rearrange that formula, again there's an example of this in your previous examples in your notes. It gets like this: x squared plus y squared minus 2y equals 0. We had a very similar one, but for it was the cos one, so it was an x here instead. The fact that half of the values of r are negative means here that the circle is described twice over. For example, the point minus 0.5 to 195 degrees is the same as the point 0.5 to 15 degrees, so it kind of goes around it twice. Final then few examples then, just so you can see. Sketch a graph of the following equations: 2 upon 1 plus cos theta, 1 plus 2 cos theta, and then 5 plus 3 cos theta. You should note that this is 2 plus 2 cos theta, where these two numbers are equal. So 2 plus 2 cos theta are equal. And this one here, this number is smaller than this one. And this one here, this number is bigger than this one. And that changes this shape, as you will see then for each of those as we kind of look through them. So let's see. For the first one, 2, 1 plus cos theta, it ends up looking like this here. And that's where the two things end up the same shape as each other. And it talks about this in the next page. It says if A equals B, if these are all lemicons, lemicon may be called a cardioid because it looks a bit like a heart shape. So this is our shape here. At the pole, the curve possesses a cusp. This is our weak cusp, and just kind of coming in here. If A is less than B, the lemicon contains a reentrant loop. So that's our situation there, where A is less than B. Too many pages here, but that's because we had the 1 plus 2 cos theta. This number smaller than this number gives us this shape here. And then if A is greater than B, it has neither a cusp nor a reentrant loop, and it ends up looking this shape here. These are all similar shapes, and you can see the formulas are quite similar, but that's how they work out. You'll notice as well, whenever they've been drawing these, it's the same format that we used, only they worked in degrees. Generally we work in radians in array level maths, but they've just worked in degrees here. But you just see they've picked various points, plotted them, and see how they work out. So those are just some examples to give you a bit of an idea about how these polar curves look.